The LM test can be used to test whether the random effects are significant or not. There are several versions of the LM test available that can be used to check the significance of random effects. The most commonly used ones are the Birch-Pagan LM test, the King, Wu, and Honda LM tests. These tests are also readily available in most software packages. Here, we will discuss the Birch-Pagan Lagrange Multiplier test for random effects. We know that if the random unobserved effects are not significant, then we can simply apply the pooled OLS model. On the other hand, the pooled OLS model will not be reliable if the random unobserved effects are significant, and we should prefer the random effects model. The Birch-Pagan LM test uses the residuals from the pooled OLS model to test the null hypothesis that the variance of random effects error is 0. In our Grunfeld example, we estimated the random effects model with only individual specific random effects or random error. In that case, we can estimate the LM statistic as shown in equation 1. In this formula, t is the number of time periods and I is the number of cross-sectional units. In the Grunfeld data we are using, t is 20 and I is 10 because we have data on 10 firms across 20 time periods. The residuals EIT are the residuals from the pooled OLS model. Therefore, this test is quite straightforward and easy to estimate because it only uses pooled OLS residuals. This LM statistic is asymptotically distributed as chi-square with 1 degree of freedom. The degree of freedom is 1 because we are testing only one restriction, that the variance of individual specific random error or sigma mu square is 0. The hypothesis of this Birch-Pagan LM test can be stated as shown here. Under the null hypothesis, the variance of individual specific random error or sigma mu square is 0, that is, individual specific random error is insignificant. As a result, we should apply pooled OLS if we cannot reject the null hypothesis. On the other hand, we should prefer the random effects model under the alternate hypothesis, which states that the sigma mu square is not 0 and individual specific random error is significant. Alternatively, we can express and estimate this LM statistic using matrix operations. It is essential to understand this because LM statistic is easier to estimate using matrix operations, and that's how it is usually handled in software programs. The formula that we discussed earlier for LM statistic in case of individual specific random effects is shown here along with its estimation using matrix operations. In this matrix formula, E cap is a n by 1 vector of pooled OLS residuals, where n is the total number of observations. In our Grunfeld example, this will be a 200 by 1 vector of residuals from the pooled OLS model. E cap transpose is simply the transpose of the E cap vector and will end up being a 1 by n vector or 1 by 200 in our Grunfeld example. I is an identity matrix of I dimensions. Here, I dimensions refers to the number of cross-sectional units, that is, 10 firms in our Grunfeld example. So, I is a 10 by 10 identity matrix. OT is matrix of ones, that is, all the values in OT are equal to 1. It is a T by T matrix, that is, 20 by 20 matrix of ones in our Grunfeld example. The operator shown here stands for the Kronecker product, that is, we estimate the Kronecker product of matrices I and OT. This Kronecker product of I and OT, along with E cap and E cap transpose, allows us to sum the residuals identical to the previous formula in equation 1. This formula in equation 2 will give us the exact same or an identical estimation of the LM statistic. It is important to note here that this LM statistic formula and hypothesis is to test the significance of the individual specific random effects only. In case of time-specific random effects or two-way random effects, this formula and hypothesis needs to be slightly adjusted. In case of time-specific effects only, we can estimate the LM statistic as shown here in equation 3. In this formula, the E cap and E cap transpose are the same as in the previous formula, that is, they are residuals from the pooled OLS model. But, the OI and IT matrices are different here. The OI is a matrix of ones with dimensions I by I, where I is the number of cross-sectional units, that is, 10 by 10 matrix of ones in our Grunfeld example. Similarly, IT is a T by T identity matrix, where T is the number of time periods, giving us a 20 by 20 identity matrix in the Grunfeld example we are using. The symbol shown here denotes the Kronecker product of OI and IT. The null hypothesis is also slightly different. Here, we are testing whether the variance of time-specific random error or sigma gamma square is 0. Under the alternate hypothesis, the sigma gamma square is significant or the time-specific random error is significant, and we should prefer the random effects model with time-specific random effects. Again, the LM statistic is asymptotically distributed as chi-square with 1 degree of freedom. For a two-way random effects model, the LM statistic formula can be adjusted as shown here in equation 4. This also uses the pooled OLS residuals E cap, same as in the individual and time-specific effects. The matrices I and OT are the same as the ones we used in the case of LM statistic for individual-specific random error in equation 2. Furthermore, the matrices OI and IT are the same as the matrices in the LM statistic for time-specific random error in equation 3. We have to be careful with the hypothesis and the degrees of freedom in this case. Under the null hypothesis, the variances sigma mu square and sigma gamma square are 0, that is, both the individual and time-specific random errors are 0. Under the alternate hypothesis, at least one of the random error variances is non-zero and the random effects are significant. The LM statistic is asymptotically distributed as chi-square with 2 degrees of freedom. You will notice that the degrees of freedom are different as compared to the earlier formulas. The degrees of freedom are 2 here because we are testing 2 restrictions that sigma mu square is 0 and sigma gamma square is 0. The application of the LM test for random effects is straightforward. In our Grunfeld example, we focused on the random effects model with individual-specific random error only. Let us continue with the same model and test whether the individual-specific random error is significant using the LM test. In R, we first estimate the random effects model using the PLM function like we did in the earlier tutorial. We specify model equals random and effect equals individual because we are estimating the random effects model with individual-specific effects only. Then, we use the PLM test function to apply the LM test for random effects as shown here. The random IND object contains the results of our random effects model. The option type can be used to select the type of LM test to apply. We have specified type equals BP for the Bruchpagan LM test. Alternatively, we can specify type equals Honda for the Honda version of the LM test, which is also the default for this PLM test function. We can also specify type equals KW for King and Wu version of the test and GHM for Gurierix version. To test for time-specific or two-way random effects, we can simply change the effect option to time or two ways while estimating the random effects model. In Stata, we can use the xtTest0 command to apply the Bruchpagan LM test for random effects as shown here. First we estimate the random effects model using the xtreg command. Then, we simply use the xtTest0 command to apply the Bruchpagan version of the test. The results of the test for random effects with individual-specific random error in our Grunfeld example are shown in the table here. We estimated the Bruchpagan version of the LM test. The test statistic is 798.16 with 1 degree of freedom. The p-value is less than 0.05, which means that we can reject the null hypothesis of sigma mu square equals 0. Therefore, the variance of individual-specific random error sigma mu square is not 0 and the random effects are significant. Hence, we should prefer the random effects model with individual-specific random error as compared to the pooled OLS model. Thank you for watching and I will see you in the next tutorial.